Good morning, all. Today we are going to learn about regular expressions and languages. See, in the previous class, we have learned about finite automata and its types. So today we are going to learn the languages of the finite automata, which is nothing but the regular language. So whenever the language is accepted by the finite automata, then we can call those languages as regular languages. And we have a simple expressions to express the regular languages that are called regular expressions. So now we'll see the formal definition of this regular expressions and the regular languages. So regular expressions are nothing but the rules that define the regular expressions over alphabet sigma are as follows. Number one, pi is a regular expression that denotes the null set. As we know, pi represents null set and the same pi is used as a regular expression to represent null set, otherwise called as empty set. Next, epsilon is a regular expression that denotes empty set that is containing the empty string. So there is a difference between pi and epsilon. Pi is a null set, whereas epsilon is a null string or empty string. Whenever the string length is 0, then will represent that as epsilon. So that is the difference between pi and epsilon. Third, if A is a symbol present in sigma, that is consider any symbol in general as A and which is present in the alphabet sigma, then A is a regular expression. So you can take that symbol as a regular expression that denotes a set A, that is a set containing the string A, the string with only one symbol A, that is the length of string is 1. See, previous length of string is 0. So whenever the length of string is 0, we can use epsilon to represent it. And for a string with a length 1, see, in general we are taking it as A. Next, we are going to build a regular expression with these basic units. Okay. So fourth one, if R and S are the regular expression. So kindly make a note that we'll be using lowercase letters in order to represent the regular expressions in general. So here R and S. So lowercase r and lowercase s are taking as two regular expressions denoting the corresponding language L of R and L of S. Then R plus S denoting R plus S denoting L of R union L of S. Clear? Then R dot S denoting L of R dot L of S. That is, so plus represent the union operator, dot represent the concatenation operator. Then R star. So R star denoting L of R the whole star. R star denoting L of R the whole star. I'll repeat. The languages that are accepted by the finite automata are called regular languages. And the simple expression used to represent the regular languages are regular expressions. Clear? So, we'll start with the basic units. So, pi, epsilon, small a are the regular expressions which represents the null set, null string and a respectively. By using these basic units, we can build a regular expressions with the operators plus, dot, star. So plus represents union operator, dot represents concatenation operator, and this power star represents closure operator. Clear? Next, we'll see, we'll write a regular expressions for the given regular languages. Okay, number one, set of strings of A's and B's of length 2. Okay, set of strings of A's and B's of length 2. So here you are going to generate a set of strings whose length is 2. I mean AA, AB, BA, BB. Okay, so this is the regular expressions used. A plus B concatenated with A plus B. So what does it mean? So in the first position you may have either A or B, and the second position you may have either A or B. So here the plus is the OR operator. Okay, so there are two symbols. Okay, so length is given as 2. The first one may be A or B, the second one may be A or B. So A plus B dot A plus B is the corresponding regular expression for set of strings of A's and B's of length 2. Next, set of all strings of 0 or more A's. Set of all strings of 0 or more A's. So that can be represented with A star. Clear? Set of all strings of 0 or more can be represented with A star. And third one, set containing the string 0 and all strings consist of 0 or more zeros followed by simple one, that is single one. Okay, that is set of strings 0 and all string consist of 0 or more zeros followed by single one. Okay, so containing 0, so 0 plus and any strings of zeros followed by a 1. Clear? So that can be represented as 0 plus 0 star 1. So suppose it should contain only 1 0. Otherwise, any number of zeros followed by 1 at the end. Clear? So either 0 or a zeros followed by single one is clear. Next. Fourth one, set of all strings 0, 1 starting and ending with 0. So starting is 0, ending is 0. In between we may have any strings of zeros and ones. So any strings of zeros and ones can be represented as 0 plus 1 the whole star. Any strings of zeros and ones can be represented as 0 plus 1 the whole star. Clear? Next problem. Set of all strings over A comma B ending with ABA. So at the end we should have a ABA. At the beginning you may have any strings of A's and B's. So any strings of A's and B's can be represented with the regular expressions A plus B the whole star. So star represents 0 or more repetitions with the symbols of A's and B's. Clear? Next. Set of all strings over A, B, C. So here you are given with 3 different symbols A, B, C containing any number of A's followed by any number of B's followed by any number of C's. Okay, the order is matter, but the number of A's and B's can be of any length. So any length in the sense 0 or more. Okay, so how can we represent that? A star followed by B star followed by C star. Clear? Next, set of all strings over A, B, C with at least one A followed by at least one B followed by at least one C. See the difference. Here any number of E is followed by any number of B followed by any number of C. But here at least one A followed by one B followed by one C. So at least one, in the sense one or more. So in order to represent one or more repetitions, we have to use positive closure. Okay, plus in the power. Okay, see A star, B star, C star. Here A to the power plus B plus C plus. So plus represent what? One or more. Star represents 0 or more. Next, set over 1 having odd length of string. Okay, so we're going to represent a string which is going to contain only 1. Okay, and that too it should be an odd number. Okay, we know that 2n plus 1. So in order to represent numbers will be using 2n plus 1. Similarly, okay, so instead of that 1, we are n, we are having 1 and 2n. So 2n in the sense 1 1. Okay, 1 1 the whole star. So it can able to produce odd length string. It can able to produce 1. So whenever you put epsilon for the star, then this becomes 1. Okay, so one time repetition, then you will be getting 3 ones. Two times repetition, then you will be getting 5 ones. Okay, it goes like that. Next, set of all strings over 0 comma 1 that ends with 1 and does not contain the substring 0 0. Okay, I'll repeat, set of all strings over 0 comma 1 that ends with 1 and does not contain the substring 0 0. So there should not be any 0 0 together. Okay, two consecutive zeros. See, for which this is the regular expression. It may have either 1 or 1 0, and this can be repeated for any number of times. Similarly, 1 0 1 or 1, this can be repeated for any number of times, and 1 at the end, because that ends with 1 is given. Clear? So 1 plus 1 0 the whole star, 1 0 1 plus 1 the whole star, and it is ended with 1. Clear? Next, set of all strings over 0 comma 1 not containing 101 as a substring. Okay, and see for which you have to give the answer. So this is the exercise problem. You do it at your home and send me the answer. Next, set of all strings zeros is divisible by, okay, divisible by 5. Okay, so all strings of zeros, okay, and when you count the number of zeros, it should be divisible by 5. So at the beginning and the end, you may have any number of ones, but in between, you should have the number of 0 which are divisible by 5. Okay, so 5 is divisible by 5, 10 is divisible by 5, 15 is divisible by 5. In order to generate that, 5 zeros go to the power plus. What does that mean? One or more repetition of this string, that is 5 zeros, clear, 10 zeros, 15 zeros, like that you can able to generate. Okay, clear? Then even number of ones, 0 star 1, 0 star 1, the whole star 0 star. Okay, so this can able to generate even number of ones along with the 0. So in the previous case, only the strings of ones, isn't it? But here set of string is 0 comma 1. Okay, but it can able to generate only the even length string. But in the previous problem is odd length, here even length. Then ABB as a substring. Okay, so ABB should come in between, and the beginning at the end you may have any strings of A's and B's. So any strings of A's and B's can be represented as A plus B the whole star. Clear? So these are all the examples of the regular languages and the regular expressions. I repeat, the languages that are represented by the finite automata are called regular languages, and those languages are represented with the simple expressions called regular expressions. So we have seen more examples over regular languages and the corresponding regular expressions. Okay. Next we'll see about the equivalence of finite automata and regular expressions. See, what is the meaning of equivalence of finite automata and regular expressions? So that too, here you have equivalence of non-deterministic finite automata and the regular expression. So the theorem is given clearly like, let small r be a regular expression, then there exists a non-deterministic finite automata with epsilon transitions that accepts L of R. So what is the meaning? If you are having a regular expression, that can be represented as a non-deterministic finite automata with epsilon transition. Okay, that is the meaning of this theorem. Let us see the proof for that. So this theorem can be proved by the induction method. So here we are going to use proof by induction method. So that the first step is to be the basic step. Okay, we have to consider the basic cases and you have to build the corresponding ENFA for the basic units of the regular expressions. Okay. So the basics of induction will be considering R has zero operators. Okay, that means R can be either epsilon or pi or a. Okay, without any operators. So the basic units. So basic units as pi epsilon a, isn't it? So for the same thing, how can you build a finite automata? That is NFA with epsilon transition that we will see now. The finite automata for the same can be written as so this is the finite automata. See here, initial state is Q naught and the final state is also Q naught, and there is no transitions. Okay, so initial state itself is the final state. Okay, this is the finite automata which can represent the string epsilon, because you are in state q naught and without reading anything you are in the final state. So what is the string accepted? Empty string is accepted. So empty string is nothing but your epsilon. Okay, and then pi. So there are two states, q naught and q1. Q naught is the initial state, q1 is the final state. Okay, so from the initial state to the final state there is no transition. So there is no transition can be represented as pi. Here there is no string, but here there is no transition at all. Here, and the next q naught is the initial state, q1 is the final state. From q naught to q1 we can transit over this a. So a is a string. After reading A, we can move from Q0 to Q1 and the string A is accepted. So how can you say it is accepted? When will you say the language is accepted? So after reading the string, when the finite automata can able to halt at the final state, then you can call the string is accepted. So here, from the state Q0, so Q0 is the initial state. After reading A, we are halting at Q1. So Q1 is the final state. So how can you tell this Q1 as final state? It is represented with a double circle. Is good. Next. So next we are going for the inductive step. So in the basic step we have seen about the basic units of the regular expressions like epsilon, pi and a. Now we are going to apply the operators too, and we are going to build the corresponding finite automata, that too non-deterministic finite automata with epsilon transitions. Okay, so this theorem can be true for n number of operators. The n is greater than or equal to 1. The n is greater than or equal to 1. So you may have any number of operators, but minimum it should have one operator. Okay. So the regular expression contains equal to or more than one operators. Yes. In any types of regular expressions, there are only three cases possible: union, concatenation, closure. So these are all the operators. Okay. So suppose you are given with union operators. Okay. So what is the regular expression with the union operator? R is a regular expression. It may connect R1 and R2. So R1, R2 are the basic units. Now the plus is the OR operator. Plus is the OR operator we are using in between. Okay. Where R1 and R2 are the regular expression. There exists two NFA for this R1 and R2, isn't it? And whose corresponding machine can be represented with a 5-tuple representation, that M1 is equal to Q1 sigma 1 del 1 Q1 F1. Clear? And the machine M2 used to represent the regular expressions. R2 is Q2 sigma 2 del 2 Q2 and F2. Okay, you know what is Q1? Q1 is set of states. What is sigma? Sigma is the set of input symbols. Del 1. Del 1 is set of, yes, set of transition function, and Q1 is the initial state and F1 is the set of final state. You know all these things already, isn't it? Okay. Now, L of M1 is equal to L of R1. So what is the meaning? The language state by the regular expression R1 is the same which is represented by M. Okay. L of M1. The language accepted by the machine 1 is nothing but L of R1. The language generated by the regular expression R1. Clear? Yes. Similarly, L of M2 is L of R2. So what is the meaning? The language accepted by the machine M2 is represented as a regular expression 2. Okay. Or else the language generated by the regular expression 2 is the language, is the same language accepted by the machine 2. Okay. Q1 represents set of all the states in the machine M1. Q2 represents the set of all states in the machine M2. We assume that Q1 and Q2 are the disjoint set. There is no there is no similarity between this Q1 and Q2. So both the sets can be called as disjoint sets. Okay. Let Q naught be a new initial state and to be a new final state, we will form, okay, so with the existing initial state and the existing final state, we are going to form a new machine M where this set of states, so the first unit is a set of states. So in the set of states, what you are going to have, Q1 union Q2 union Q naught F naught. So what does it mean? So we are going to build a new machine M for which these are all going to be the states. All states from Q1. Okay. All states from Q2. And along with that, we are going to introduce two more states, that is Q0 and F0. Clear? And the input string is union of this sigma 1 and sigma 2. Then del we are going to define later. And the initial state of the entire machine which we are going to construct for R1 plus R2 is going to be the new state which we have introduced Q0, and the final state is the F0, that is a new state we have introduced. Okay. Apart from that, the del is going to include Q0 comma epsilon is equal to Q1 and Q2. So from the state Q0 for the epsilon, we have to make a transition to Q1 and Q2. Okay. And then any Q comma A is going to be the Q comma A. So that is already defined in del 1. Similarly, any Q comma A also it is defined in Q2. So Q2 for small q and Q1 minus F1. So here you just taking out this F1 and A in sigma 1 union epsilon. So you may have some epsilon also. Then F1 comma epsilon and also F2 comma epsilon is equal to F0. So we have to connect this F1 and F2 through epsilon to this F0. Okay. So all the moves are now represented in the machine M, which is as given below. So look at here. We have M1 with some set of states. Here you know clearly about the initial state and the final state, and also another machine Q2, another machine M2 with the initial state Q2, final state F2. Okay. So using these two machines, finite automata M1 and M2, we are going to build a M. We are going to build a M. Okay. M is the machine. M is the machine. Clear? So new machine which can accept the string R1 plus R2. Okay. So for that, how can you build? You have to introduce new initial state and new final state. So that is what here set of states includes Q0 and F0. Okay. Yes, we have added two more states Q0 and F0. Then we have introduced the transition. So look at here, we have introduced the transition Q0 comma epsilon is equal to Q1 Q2. So what is the meaning? Q0 from Q0 to Q1, from Q0 to Q2, there is a transition for epsilon. Okay. And also we have included that F1 comma epsilon, F2 comma epsilon is equal to F0. So F1 comma epsilon, F2 comma epsilon is equal to F0. Okay. By using the basic machines or the finite automata M1 and M2, we have built a machine for R1 plus R2. So R1 is the regular expression accepted by this M1. R2 is the regular expression which represent the regular language which is accepted by this M2. Clear? The construction of machine M is showed. The transition from Q0 to F0 must begin by going to Q1 or Q2 on epsilon. If the path goes to Q1, then it follows the path in machine M1 and goes to the state F1 and then goes to the F0 on epsilon. Similarly, if the path goes to Q2, then it follows the path in the machine M2 and goes to the final state of the machine M2, that is F2, and goes to the F0, that is the final state of the entire machine. Thus, L of M is equal to L of M1 union L of M2. That means either the path in machine M1 or M2 will be followed. Clear? Then we'll see about the concatenation operator. Okay, so case 2. Let R is equal to R1 dot R2, where the regular expression R1 and R2 are the two regular expressions. The machine M1 and M2 denotes the two machines such that L of M1 is equal to L of R1 and L of M2 is equal to L of R2. So now we are going to build a new machine M as Q1 union Q2. Okay, so Q1 union Q2. Then sigma 1 union sigma 2 del Q1 F2. So the new initial state is Q1, the new final state is Q2. Okay. The mapping function del can be given as, so all the transitions, that is del of Q comma A, okay, is equal to del 1 of Q comma A. Then F1 comma epsilon is equal to Q2 Q comma A. So we'll see the new machine that we are going to construct for this concatenation operations. So we're taking two machines, Q1 and F1 are the initial and final state of this M1. Okay, M1 going to accept the regular language L of R1. Okay, M2 is a finite automata which is going to accept the regular language L of R2. Okay, now we are going to build L of R1 dot L of R2. So concatenation. Okay, so what we are going to do, we are going to connect the final state of the machine 1, that is F1, with the initial state of machine M1, M2, okay, which is nothing but Q2, through epsilon. That's it. So this is the new transition we are going to include for making the machine M for the concatenation operation. Okay, that is the initial state is Q1. By some input A, the next state will be F1, and on receiving epsilon, the transition will be from F1 to Q2, and the initial state will be F2, and the final state will be F2, the entire final state. And it can go on some input B. Thus, L of M is equal to AB. So here we're just taking one example. So you consider this as a machine which is used to accept A, and this is the machine which is used to accept B. Then after reading A, you can be here. Without reading anything, you can jump to this initial state. Then you can read this B, then you can go to F2. So that AB is accepted. So A is accepted by this machine 1, M1, and B is accepted by M2. So altogether, after reading AB, we can go to the state F2, and this AB is accepted, isn't it? So thus, what you can able to conclude, A is in L of M1, B is in L of M2. Thus, L of M is equal to L of M1 dot L of M2. Clear? Next. Case 3. So here we are going to discuss about the closure operator. Let R is equal to R1 star, where R1 be a regular expression. The machine M1 is such that L of M1 is equal to L of R1. Clear? So we are going to let the regular expression R1 over which we have to apply the operator, clean closure operator, that is star operator. Okay. where this R1 has become R1 is a simple regular expression, any regular expression. Okay, then we are taking a machine M1, okay, which is going to accept the L of R1. Okay, then we can construct a new machine M such that Q1, all the states of the machine 1, union two more states, Q0 and F0, comma, sigma. Okay, sigma 1, we are going to update it as sigma 1 and some del. Okay, del is the transition function we are going to define later. Then the initial state as the Q0. Q0 is a new state which we have added, and F0. F0 is a one more new state which we have added. Okay. So then mapping function del Q0 comma epsilon is equal to Q1 comma epsilon is equal to Q1 comma Q0. Then Q0 comma A. So all the transitions already in the machine M1. And F1 epsilon is going to be Q1. That is so here. So you have a finite automata M1 which is going to accept L of R1. Okay. We're going to take as such. Then what you're going to do? You're going to introduce two more states, Q0 and F0. So Q0 and F0 are two more states. Okay. So from the state Q0 to the state Q1. So Q1 is nothing but the initial state of the machine M1. We are going to draw a transition over epsilon. That is, we are going to connect the new initial and the initial state of M1. Similarly, we are going to connect the final state with the new final state which we have introduced through epsilon. And also we have to connect Q0 and the F0, the new initial state and new final state of the machine M. And also, so you know the star operators tells 0 or more. Okay, so by connecting this Q0 to Q0 to F0, we can able to accept this epsilon. Okay, so 0 times 0 or more. So in order to read the a regular expression or the regular language of this M1, that is L of R1, repeatedly, what we are going to do, we are going to draw epsilon transition from F1 to Q1. F1 to Q1. So, this is to repeatedly read the strings of L of R1. Clear? Yes? Is it clear? Okay. The machine M shows that from Q0 to Q1, there is a transition on receiving epsilon. Similarly, from Q0 to F0 on epsilon, there is a path. The path exists from F1 to Q1. Okay, a back path on epsilon. Similarly, a transition from F1 to F0 on receiving epsilon. Clear? The total recursion is now possible. So now L of M is equal to L of M1 star. Clear? Okay. Next we will see some examples for how to construct NFA with epsilon transition whenever you are given with the regular expressions. So look at here. You have given with B plus B A star. Okay. So B is one regular expression. Again, B A star is another regular expression, and these are all connected with a plus operator. Okay. And when you see this R2, suppose if you are assuming this R1 as B and R2 as B A star, so this R2 has the operators dot as well as the closure. Okay, so how can we draw it for this? Okay, so first you have to take the basic units separately. So this is for B. Okay, so from 1 to 2 you can go through. This is the finite automata which can accept B. And for A star, okay, so how to draw it for A star? First you have to draw for A, then you have to connect the final state of A to the initial state and new initial with the new old final. So these things you have to do. Okay, so come here. This is the 4 and 5 represents finite automata for A. Then you have to connect the initial state 3 and 4 through epsilon and 5 and 6 through epsilon, and also 3 to 6 the initial state, the new initial state and the new final state through epsilon, and for the repetition 5 to 4. Clear? So that you have got for B and A star separately. Now you can build B dot A star. So B dot A star is disconnect this B with the A star. Okay. So with that, what you are supposed to do, you have to connect the final state of B to the initial state of A star. Okay, that is what we have combined both the things. Okay, and then B plus B A star. Okay, either or part. So here from 9 to 10 you can go when you if you want to read B, and for this B A star you can follow this path, that is this from 7 to 6. Okay, and both the things are connected with the new initial state 9 and the new final state 10. Is it clear? Yes. So similarly, note down these problems and solve at your home as a homework. Okay, note it down. 0 1 plus 1 0 the whole plus 0 1 plus 2 star into 1. So here there are three inputs 0 1 2. Okay, and then a into a plus b the whole star b plus a b star a the whole star. So for which what how can you draw? First you have to draw a the whole star. Connect them with a and b. So append a in the beginning, append b at the end. And also another machine a b star b. Okay, then you can perform union operator over which at last you have to give this star, because the precedence are most important. Always open parenthesis close parenthesis takes the highest precedence, then the star, then dot, then plus. Okay, so please kindly consider the precedence while you are drawing this NFA with epsilon transition. Next, 1 plus 0, 0 star 1, 0 star 1, 0 plus 1, 0 star 1 the whole star. So all those things. Okay. Shall we move to the next topic? So next topic is equivalence of GFA and regular expression. So what is the previous topic? Can anyone tell? What is the previous topic? Equivalence of finite automata, regular expression and the finite automata. That is, whenever you are given with the regular expressions, what you can able to convert, you can able to convert it to a ENFA. That is NFA with epsilon transition. So now, for the given finite automata, how can you give the regular expressions? Okay, that will see. Here, if L is equal to L of A for some D of A, then there exists a regular expression or such that L is equal to L of R. So what is the meaning? So you are having a language L and the language is accepted by the finite automata A. Then if so, you can represent that regular language as a regular expression. The language accepted by the finite automata A can also be represented as the regular expression R. Okay. So whenever you are given with the finite automata, how can you convert it to a regular expression? So that is equivalence of GFA and regular expressions. We'll go to the proof. Let us suppose that A's states are, so we are going to have a finite automata capital A and whose states are 1, 2 and so on n for some integer n. Let us use Rijk as the name of the regular expressions whose language is set of strings W, such that W is the label of the path from state I to state j in capital A, and that path has no intermediate node whose number is greater than k. Okay, so we're going to have a regular expression Rij power k. So I is the any initial state we are going to consider, and j is the any final state which we are going to consider, and ka is the all the set of intermediate nodes. Clear? A path whose label is in the language of the regular expressions. Okay, so travel along the path from I to j via some states. So via some states are nothing but some k. Okay, for which you are going to start from the state 1 to n. So consider there are some n states. Okay, ij to be the greater than k. Always is ij to be greater than k, but either or no or both could be k or less. Okay, to construct the expression Rijk, we use inductive definition starting at k is equal to 0 and finally reaching k is equal to n. So k is equal to 0. What is the meaning? Without any intermediate node in between. Okay, that is going to be the basic step. So here we are going to use proof by induction method. Okay. So since all the states are numbered 1 or above, the restriction on the path is that the path must have no intermediate nodes at all. Okay, there are only two kinds of path that meet such a condition. An arc from the node I to j, the path length 0, that consists of only some nodes I. Okay, so for that case 1, if I is not equal to j, if there is no symbol like a, then rij will be your pi. So there is no transition now pi, isn't it? If there is exactly one symbol a, then you can represent it by a. If there are symbols, so you may have more than one symbol also from I to J. So how can you represent those symbols with the OR operator? So either A1 or A2 or and so on AK. Okay, so there are more symbols from I to J. How can you represent A1 plus A2 and so on AK? Okay, then case 2. Whenever this I and J are equal to each other, so whenever you are in state, you are after reading something, you are in the same state. So what is the string which you have read? Null string. Okay, you are in this state and you are in the same state. Okay, I and j is going to be the same. Then you can represent it as epsilon. Or else, if you are having some transition over it, so I over at A. So that can be represented with the epsilon or A. So what is the meaning? Without reading anything, you can be in the same state. Or for reading A also, you can be in the same state, isn't it? So epsilon plus A. Or else, so instead of having only one symbol, suppose you are having more than one as A1, A2 and so on AK. So how can you represent epsilon plus A1 plus A2 plus and so on AK? So these are all the basic steps. Okay. Then we'll move to the okay. Suppose there is a path from state I to j that goes through no state higher than k. There are two possible cases to be considered. The path does not go through the state k at all, or the path which goes through k. Okay. See, there may be a path from this I to j straight away, or else you may have a path via this k. So you have two options. The first piece goes from I to k without passing through k. Okay, without passing through. So there is no self loop for k. So that can be represented r I k minus 1. And the last piece is nothing but r k r k minus 1 kj. Okay, so from I to k, k to j. And this is for repetition. So how can you represent this repetition? R k minus 1 the whole star. Isn't it? 0 or more. Clear? So how can you conclude? And all the pieces in the middle go from k to itself without passing through k many passing through the k for many times. If so, how can you represent r k minus 1 the whole star? Okay. The set labels for all parts of this type is represented by the regular expression r I to k minus 1 dot r k minus 1 the whole star dot r k minus 1. Okay. We combine the regular expression for the path of two cases above. We have the regular expression. So one is, the first one is without going to k, which is nothing but there exists a path from I to j with the intermediate node. The previous intermediate nodes are nothing but k minus 1. Okay. For the labels of all paths from state I to j that goes through no state higher than k. The regular expression for the language of automation is thus the sum of all expressions are ij whole to the power n such that I is the start state, j is the accepting state, and n is the number of nodes. Okay, k is equal to n that we have seen already. Isn't it clear? See, for which we'll see one example. Convert the following to the regular expression. Clear? So we are given with a finite automata. Okay. So 1 for 0 goes to 2. 1 for 1 remain in same state. And 2 comma 0 is 2. 2 comma 1 is 2. And for which you have to build the regular expressions. Okay. As we know, we have to start with the basic step, which is nothing but k is equal to 0. R11 power 0 is equal to epsilon plus 1. R12 power 0 is 0. See, whenever I is equal to j. So first R11, okay, from 1 to 1. From 1 to 1, we have one self loop. But whenever I is equal to j, you have to include epsilon also. So this R11 power 0 becomes epsilon plus 1. And similarly, R1 to 2. So 1 to 2, I is not equal to j, but you have 0. So 1 to power 0 is 0. So what does a 0 represent here? R1 to power 0. 0 now, what is the meaning? It's an intermediate term. So we are not going to consider any intermediate term. That is the meaning. Okay. Then 2 1. There is no transition from 2 to 1. So how can you represent no transition? Pi. Then, so R2 to 0. 2 2. So I is equal to j. So epsilon plus 0 plus 1. Okay. Next, if k is equal to 1. Rij power k. So you have to go with the formula. So Rij power k is equal to Rij k minus 1 plus Rik k minus 1 dot Rkk k minus 1 the whole star dot Rkj k minus 1. Clear? Yes. So here, what we are going to find out? R11 power 1, R12 power 1, R21 power 1, R22 power 1. So first we'll find out R11 power 1. So by applying this formula, this R11 power 1 can be written like R11 power 0 plus R11 power 0 dot R11 power 0 the whole star R11 power 0. So already we have got answer for this R11 power 0 as epsilon plus 1. So substitute that. Epsilon plus 1, here epsilon plus 1 dot epsilon plus 1 the whole star epsilon plus 1. See this entire thing can be simplified as epsilon plus 1 the whole star. And this entire thing can be simplified as epsilon plus 1 the whole star. So epsilon plus 1 the whole star is 1 star. Clear? So what is the meaning? Either epsilon or 1, and this can be repeated for any time. So that is similar to 1 star. So 1 star include epsilon, isn't it? And similarly, then we have to find out R12 power 1. So how can we find out R12 power 1? Use the same formula. R12 power 1 can be written like R12 power 0 plus R11 power 0 dot R11 power 0 the whole star R12 power 0. Okay. So what is R12 power 0? Get from the previous, that is 0. Okay, and R11 power 0 is epsilon plus 1. Then epsilon plus 1 the whole star, 0. So this content can be represented as 1 star 0. So 0 plus 1 star is nothing but 1 star 0. So how can you take this 0? See, what is the meaning of this expression? Either 0 or any strings, any strings of 1 followed by 0. So here, both the cases we can able to get the 0. So that you can simplify this as 1 star 0. Okay, so each and every step we have to simplify the regular expressions which are we are obtaining. Okay, next what we are supposed to find out, R21 power 1. R21 power 1 is what? Here substitute the formula, then you'll be getting R21 power 0 plus R21 power 0 dot R11 power 0 the whole star R11 power 0. Okay, so we know R21 power 0 is pi. Okay, so pi plus pi dot epsilon plus 1 the whole star epsilon plus 1. Anything concatenated with pi is pi. So pi plus pi you will be getting pi. So the answer for this R21 is pi. Next, R22 power 1. So R22 power 1, R22 power 0. So expand the formula and write like R22 power 0 plus R21 plus 0. R11 power 0 the whole star R21 power 0. Okay, now substitute the value. Epsilon plus 0 plus 1 plus pi dot epsilon plus 1 the whole star dot 0. So whenever you concatenate any regular expression with the pi, you will be getting pi. But this side with the R operator you have epsilon plus 0 plus 1. So R22 power 1 is epsilon plus 0 plus 1. Okay. But what is the final answer for this diagram is R12 power 2. So how many, the total number of states is 2. Okay, so up to this we have got answer for power 1, isn't it? K is equal to 1. So now we have to find out for k is equal to 2. Okay, so k is equal to 2. 1 to power 2, 1 2 1 2 1 1 part 2 1 2 part 2. Actual answer is actually 1 2 part 2 because the initial state is 1 and the final state is 2. So no need to find out R11 power 2. You straight away can find out R12 power 2. Excuse me. Okay. Next we'll check the answer for R12 power 2. Expand this R12 power 2 as 12 power 1 plus 12 power 1 22 power 1 the whole star 2 to 1. Substitute all the values from the previous calculation, k is equal to 1. Okay, so 1 star 0 plus 1 star 0, epsilon plus 0 plus 1 the whole star, epsilon. So this entire thing can be represented 0 plus 1 the whole star. Okay, and here 1 star 0. So both the side you have 1 star 0, you can simplify as 1 star 0, 0 plus 1 the whole star. So go to this diagram. Is this the regular expression you are getting? Yes. Look at here. So you can read this 1 for any number of times. How can you represent? So 1 star followed by 0 followed by 0 plus 1 the whole star. So this is the final answer we have got by following the formula for RIJK. So 1 to part 2 was 1 star 0, 0 plus 1 the whole star. Clear? Okay, next we'll see another example where we are having two final states. So in the previous case, we had only one final state. So suppose we are given two final states. So then how can you find out the regular expression? That we'll see now. Okay. So here Q2 is one final state and Q3 is another final state. So what you are supposed to do, you have to consider Q2 as a final state separately and Q3 as a final state separately. Then you have to write the regular expression obtained with the plus operator. So either or. Okay. So I mean we have to find out R12 power 3 plus R13 power 3. That is, there are three states totally. So power should be 3. And initial state is 1. And final states are two states, Q2 and Q3. So initially 1 to 2 power 3 plus 1 to 3 power 3. Okay. So always we have to start with the basic step. P is equal to 0. So what is R11 power 0? So 1 to 1, there is no explicit transition. So that whenever I is equal to j, by default we have to put epsilon. Okay, then 1 to 2 is 0. 1 to 3 is 1. Okay, then 2 to 1, 2 to 1 is 1. 2 to 1, isn't it? 2 to 1 is 0. Okay, good. 2 to 0 is, so 2 to, there is no explicit transition. So what you can write? Epsilon. So you have to be very careful and you have to check whether I is equal to j or not. Whenever I is equal to j, by default you have to put epsilon, and if there exists any explicit transition, you have to include that also. Okay. So 2 to 3. 2 to 3 you have 1. Okay. Then 3, 1. 3 to 1, there is no such. So there is no transition can be represented with 5. 3 to 2 is actually 0 comma 1. Okay, so here it is written like 0 comma 1. So 0 comma 1 in the sense in the regular expression you can write 0 plus 1, isn't it? Next 3 3. 3 3, there is no explicit. So whenever I is equal to j, by default you have to put epsilon. So that you have to write. Then whenever k is equal to 1, all the combinations. Since there are three states, you will be getting 9 combinations. R11, R12, R13, R21, R22, R23, R31, R32, R33. Clear? So 9 combinations you will be getting. Okay. So now find out R11 power 1, which is nothing but you have to expand the formula. R11 power 0, R11 power 0, R11 power 0 the whole star, R11 power 0. Okay, then epsilon plus epsilon dot epsilon star epsilon. Okay, which is nothing but epsilon. R12 power 1, R12 power 0 plus R110 dot R110 the whole star dot R12 0. 0 plus epsilon dot epsilon star 0. 0 plus 0. Clear? Yes. Next, R13 power 1. So expand the formula and write like R13 power 0 plus R11 power 0 dot R11 power 0 the whole star dot R13 power 0. Substitute the previous value which we have obtained like 1 plus epsilon dot epsilon star 1, which is nothing but 1. Clear? Next, R21 power 1. Expand the formula and write like R21 power 0, R21 power 0 dot R11 power 0 the whole star, R11 power 0. Okay. Next, 0 plus 0 dot epsilon. Okay. Which is nothing but 0 plus 0. 0 plus 0 in the sense 0 only. Okay. Next, R22 power 1. R22 power 1 can be written like R22 power 0 plus R21 power 0, R11 power 0 the whole star, R12 power 0. Next, substitute the values from the previous computation as epsilon plus 0, epsilon star 0, which is nothing but epsilon plus 0, 0. Clear? Next, R23 power 1, which is equal to R23 whole power 0 plus R21 power 0 dot R110 the whole star R13 power 0, which is nothing but 1 plus 0 epsilon star 0, which can be written like 1 plus 0, 0. Next, R31 power 1 is R31 power 0 plus R31 power 0, R11 power 0 the whole star, R11 power 0. Substitute all the values. So here we are concatenating pi with other regular expressions so that you can straight away write pi. Next, R32 power 1, which is nothing but R32 power 0, R31 power 0, R11 power 0 the whole star, R12 power 0, which is nothing but 0 plus 1. Next, R33 power 1. So R33 power 0, R33 power 1, R11 power 0 the whole star, R13 power 0. At last you have got epsilon. So whenever k is equal to 1 is over. Next what you have to find out? K is equal to 2. Okay, find all values for k is equal to 2. Because the final is R to the power k is equal to 3. Okay, you have to find all the values of k is equal to 2 also. So for 2, you can substitute the 1's value. Okay, so R11 power 2 is nothing but R11 power 1, R12 power 1, R22 power 1, the whole star, R21 plus power 1. Okay, substitute the value and you can write it as 0, 0 star. And R12 power 2 is 0, 0 the whole star. 13 power 2 is simplified as 0 star 1, and R21 power 2 is simplified as 0, 0 star 0. Then R22 power 2 is 0, 0 star. 23 power 2 is 0, 1, 0 star 1. R32 power 1 is 0 plus 1 the whole star, 0, 0 star 1. And then R32 power 2 is 0 plus 1, 0, 0 star. R33 2 is epsilon plus 0 plus 1 the whole star, 1. Okay. Next, you are supposed to find out 1, 2, 3 and 1, 3, 3, isn't it? So this 1, 2, 3, expand the formula. Then you will be getting R12 power 2 plus R13 power 2 plus R33 power 2 the whole star, R33 power 2. And get the value from the previous calculation and substitute 0 dot 0, 0 the whole star plus 0 star 1 dot epsilon plus something the star, then 0 plus 1. So you just keep and you can simplify it as 0 plus 0 star 1 because the 0 star is repeated here and here. Okay, so you can write in one places. Similarly, this R13 power 3 can be written like 0 star 1, 0 plus 1, 0 plus 1. Okay. At last, we have to combine both the things. Okay. So that you can get the answer like this. So this is the regular expression for the given corresponding finite automata. Okay. And take down this problem and you can solve it as a homework. Here you are given with 3 states, 1, 2, 3, but here you have only one final state. So what is the final answer you have to compute? R 1, 2, 3. Initial state is 1, final state is 3. The total number of states should be in the power, isn't it? So R1, 3 whole to the power 3. How can you do? First you have to compute when k is equal to 0, k is equal to 1 and k is equal to 2. At last, substitute all the obtained value. Then you can go with this R13 power 3. Okay. And one more problem, make a note of it. Here also there are 3 states. but only one state as a final state. So what is the solution you have to find out? R13 power 3, because total number of states is 3. Initial state is 1, final state is 3. Clear? Do these problems as a homework. Okay, we'll see the last topic under this regular languages and expressions. Okay, proving languages not to be regular. So pumping lemma for regular languages. The statement is given like, let L be a regular language, then there exists a constant n which depends on L such that for every string W and L such that length of W greater than or equal to n, we can break W into 3 strings. W is equal to x, y, z such that y is not equal to epsilon and length of xy is less than or equal to n. For all k greater than or equal to 0, the string xy par k that is in L. Okay, that is repeating y any number of times or deleting it. The case k is equal to 0 keeps the resulting string in the language. So what does it mean? Whenever you are given with a language, and suppose if you want to prove the given language is not regular, what you can use this pumping lemma. So for that, first you have to consider the given language as regular. Okay, then by using proof by contradiction method, you can take any strings of length greater than or equal to n. So you have to consider n as a given constant in that problem. Okay, and you have to take a string whose length should be greater than or equal to that n. Okay, then you have to divide the string into 3 pieces, x, y, z. Okay, while dividing we have to consider some conditions. So what are the conditions you have to check? The y is not equal to epsilon. I mean the length of y is not equal to 0. Okay, you should have something as a y, and the length of xy. So the length of xy should be less than or equal to n. So meaning it is not too far away from the final state. Okay. And then when you repeat the middle portion, so you have taken something as y, isn't it? When you repeat it, it should belongs to L. If these 3 conditions satisfy, then we can say the language is regular. But we are going to use proof by contradiction method. So any one of the condition, so the last condition cannot be hold for the given situation, so that you can conclude our assumption is wrong. So what was our assumption? Let L be the regular language. So that assumption is wrong. So that what you can prove? The given language is not regular. So whenever you are supposed to prove the given language is not regular, you can use this pumping lemma. So I'll repeat this theorem. Let L be a regular language, then there exists a constant n which depends on L such that for every string W and L such that length of W less than or equal to n, we can break W into 3 strings such that W is equal to xyz such that y is not equal to epsilon, length of xy is less than or equal to n. For all k less than or equal greater than or equal to 0, the string xy par k z is also in L. So repeating y any number of times or also deleting it. So deleting it is when the k is equal to 0. So it should belong to L. Okay. So by breaking the third condition or by making the third condition as a false, what we can prove, the assumption is wrong and the given language is not regular. And one more thing you have to make a note. In order to prove, you cannot use this theorem. In order to prove the given language is not regular, you can use this pumping lemma. Clear? Any doubts? Okay, students. Thank you so much. The next class will start with the next set of language called context-free language and the corresponding representation context-free grammar. Clear? Thank you, students.